Let's continue with this section on algorithms. So remember, an algorithm is just gives precise instructions for performing a computation or a task. So the next task is sorting. We've already seen that lists are easier to search if they've been sorted, if they're in order. Alright, so this is an important topic. So how do you sort a list? So what's a good way to put a list, say, of numbers in order? Well, one way is the bubble sort algorithm. Alright, so this is a very simple way, easy to program. So the bubble sort just goes through a list and switches pairs that are out of order. Alright, so if you go through a list switching pairs that are out of order, you'll improve the list, but it won't sort the entire list, so you have to do a second pass, then a third pass. So repeat this switching until the list is sorted. So let's see how it works with a short list, so just these four numbers. Okay, so we want to sort these. That means putting them into increasing order. So we want it to go from smallest to biggest. So let's write the list vertically instead of across. Okay, so we have 52, 90, 13, and 40. So in the first pass, so going through the list the first time, okay, so first we compare the first two. Okay, so 52 is less than 90, so we don't need to change these. Okay, now we compare the second and third, and these are out of order. So put the arrows here, so we are going to switch. Okay, so switch these two, we get 1390, and then move to these two. The 90 is too big, so we're going to switch these. Alright, so this means don't switch, this means switch or interchange. Alright, so after the first pass, our list now looks like this. The 90 is definitely in the right place. Okay, so after the first pass, so the biggest number is going to end up at the bottom. But the rest of the list is not in order, so we need to go through the list again, but we can ignore that last element. We know that's correct. So now we're just sorting these three. So again, start at with the first two. We do need to switch these. And then, we do need to switch these as well. Alright, so after the second pass, now the 52 is also in the right place. So these two are correct. These are also correct, but in general, we'd have to check these. So third pass, just checking these, and so these two we don't need to change. Alright, so So these three are now correct, and yeah, this first one's also correct. Alright, so you see how this bubble sort works? Yeah, it's like the smaller numbers bubble to the top and the bigger ones sink. And this is the answer. And we had to go through the list 3 times. So a list of 4 elements. Yeah, so if there was a list of 10 elements, we'd have to add 9 passes. All right, and here's the algorithm in pseudocode. Okay, so remember from last time our kind of fake programming language. All right, so call it bubble sort. Okay, so the procedure takes in this input, A1, A2 up to AN, real numbers. And so this is an unordered list we want to sort. All right, the outer loop goes from 1 to n minus 1. Okay, yeah, so the I stores the number of passes. So when I is 1, we're doing the first pass. And then J is stepping through the list. So when I is 1, J is going from 1 to n minus 1. And it's just comparing AJ with AJ plus 1. Yeah, that's J going from 1 to n minus 1. So here on the first pass, I is 1. This comparison here, this is when J is 1. We're comparing A1 and A2. And this is when J is 2, comparing J2 and J3. And this is when J is 3. And if you do have a pair that's out of order, then just switch that pair. Where switching means AJ takes the value of AJ plus 1, and AJ plus 1 takes the value of AJ. Alright, so once J's got to the end, n minus 1, then this loop finishes, and we're back to the I loop, so then I becomes 2 here in the second pass. And notice here in the second pass now, J is just going from 1 to n minus 2. Alright, so so here J is 1, here J is 2. We don't need to check these two, we know that the last guy's in the right place. So these J loops get shorter. Alright, so it has the advantage of being very simple, so just 3 lines of code. But yeah, bubble sort is not very efficient. There are faster ways to sort. So another way here is insertion sort. I'm not sure if this is much faster, but we get a different method. And the way this one works is by first sorting the first part of the list, and then looking at the next number in the list, and then putting it in the right place in the part of the list that's already sorted. And how do you find the right place? Well, that's just using a simple linear search, just comparing the new element with each element in the list starting at the beginning. Example 2, yeah, let's take the same list and see how the new method works to sort it. Alright, so again, yeah, just in words. So at the start, yeah, this first number, yeah, think of it as a list of one element. Yeah, there's only one number, so there's nothing to sort. And the next number, 90, well, if we add 90 to this list, should it go in the front or on this side? Yeah, so it should go on this side to be in the right place. So in other words, yeah, we don't need to move that 90. Alright, so now these first two are sorted. Look at the next number, 13. So where does the 13 go in this list? Well, yeah, it has to go at the beginning. And finally the 40, and that should go between the 13 and the 52. Alright, so that's how the insertion sort works. Yeah, also pretty simple in words, although to program it's a bit more complicated. So our outer loop is going to be a J loop, and it decides where to insert the jth element, a sub j. Okay, so midway through the procedure, you've got the first j minus 1 element sorted, and you have to figure out where to put a sub j. Okay, that's going to be, we'll use this while loop to figure out where to insert. And this is just a linear search, if you remember from last time. So we start with I equals 1. If this aj is bigger, strictly bigger than a1, then we move to the next. Okay, I increases by 1. Is j strictly bigger than a2? Well, eventually this condition has to become false. Certainly it's false if I is equal to j, but before that you could find some ai that's greater than or equal to a sub j, so that's going to make this false. Alright, so that tells us that, yeah, we need to put the aj in here before that ai. Okay, so how do we actually do the insertion? Oh, that's also slightly complicated. So we store the value of a sub j in a new variable m. And then we so then basically we want to move all of these guys up one, and then put the aj in here. Okay, so let aj equal aj minus 1, then let aj minus 1 equal the one before, down to a sub I plus 1 equals a sub I, and then let a sub I be that m, the old aj. Alright, so that's what this k loop does. It's just shifting all these guys up so we can fit in the a sub j here. And so it's kind of a clean way to do it is k stepping from 0 to j minus I minus 1. So in the first step, when k is 0, then aj is equal to aj minus 1, that assignment. So that moves this value up to here. When k is 1, aj minus 1 is assigned aj minus 2. Alright, so they all get shifted down to ai plus 1 is equal to ai. So when you're dealing with lists, then it's lots of indices to be careful with. Okay, so this is how you program an insertion sort. I think it's a bit more efficient than bubble sort. Bubble sort, very simple, not very efficient. Insertion sort, it's more efficient but more complicated. The best sorting algorithms are this merge sort works by breaking up the list in two and sorting each piece, each half, and then merging. And so that's a much more efficient way. It's more complicated. It uses this idea of recursion. We're not looking at, but that's covered in csi30. We're just looking at more basic algorithms here in this introduction. Okay, another class of fairly simple algorithms are called greedy algorithms. Okay, so they work step by step, and just at each step they make kind of a local optimization. They just do the simplest thing, kind of to maximize something. For example, suppose a company is trying to make as much money from its customers as possible with certain constraints. So if you're trying to maximize or minimize something, that's called an optimization problem. suppose this company has figured out an algorithm that solved this problem, say using 100 steps. The algorithm is called a greedy algorithm. If it tries to get the most money possible at each step. Alright, so this kind of greedy algorithm, it might not give the very best solution, but it's going to give you some kind of solution. You're trying to improve your profits here. Alright, let's see an example. Example 3, give a greedy algorithm to make n cents in change using as few coins as possible. The coins here are quarters, dimes, nickels, and pennies. So we can see the steps here. I'm sure you've used these steps. Okay, yeah, here n is any number of cents. So first start with the quarters. So use as many quarters as possible. Okay, so you can see that's a greedy step. We're just use as many quarters as possible. Step 2, so whatever's left, use as many dimes as possible. Step 3, the nickels, and step 4, the pennies to finish making the change. Alright, so yeah, it's a greedy algorithm because at each step we're doing a maximum, so the most nickels possible in step 3. And you can see that will work, so that will make the change using as few coins as possible. You could make the change just using pennies, but that's going to use much more coins than you need. Instead of using these coins, you could think of the general problem where you have coins of different sizes. Yeah, let C1 be the number of cents for the biggest coin, and then a strictly smaller coin, C2, down to CR. So how could you make change with these coins? Again, using the smallest number of coins possible. Okay, so again, we want to make change for n cents. And the solution tells us, the answer we're looking for, how many of these C1 coins should we use? So that'll be the number D1. How many of the second type of coin, C2, should we use? That'll be the number D2 in the output. Okay, D3 down to using DR of the CR coins. So here is that, again, the obvious greedy algorithm. Procedure change. With this input, the coin types, and n is the change we're trying to make. Yeah, these are positive integers, and C1 is the biggest coin type. So decreasing order. Okay, so yeah, one way to do it, yeah, so I is looping from 1 to R. Okay, so we're going to start with the C1, the biggest coin first. Okay, so when I is 1, so D1 is going to keep track of how many of these C1 coins we need. So we're using a while loop. While n is greater than or equal to C1. Okay, so n is going to be the amount of change left to put into coins. So while n is more than the size of this C1 coin, then do this. Well, we're going to use one of those coins, so n goes down by C1, and then this counter goes up, so D1 becomes, gets increased by 1. Okay, then just keep doing this, keep using another C1 coin until this becomes false, until n is less than the value of C1, so you can't use C1 anymore. And then you go to the next coin, I is 2, and we look at C2. And again, the counter for the C2 coins is D2, that gets initialized to 0, and the same procedure. And the loop goes to I goes as far as R, so then you see how many of the last type of coin you can fit. And so yeah, if you're dealing with pennies, then you can make the whole n completely, but yeah, if it's CR is not equal to 1, then yeah, it might not be able to make complete change. Alright, so let's see an example of that in action. And again, yeah, so the output is these D1, D2 up to DR, telling you what the change looks like, how many of each coin. Okay, so a typical kind of question is to, yes, show the steps used by this change procedure to make 70 cents in change using coins of size. So C1 is 12, so we have 12-cent coins, 7-cent coins, and pennies. Alright, so we have R is equal to 3, N is 70, I starts out at 1, and D sub 1 starts out at 0. Okay, then this while loop. So first we check this condition. Is 70 greater than or equal to C1? True. So we do these two steps. D1 gets increased by 1, and N gets decreased by 12. Okay, now back to the start of the loop. Is N still greater than or equal to C1? Yeah, N is 58, so that's still bigger than 12. So repeat. It's going to keep repeating. Eventually D1 is 5. So if you use 5 of these 12-cent coins, then the change left is 10. Is 10 greater than or equal to 12? So now that's false. So now we finish this loop. Okay, we're done with the C1 coins. Now in the main loop, now I becomes 2. Okay, I is 2, D2 starts out at 0, and greater than or equal to, this time 7 is true. So increase D2 by 1, decrease N by 7. And now the condition is false, so this loop ends. 3 greater than or equal to 7 is false, so we can't use any more of the 7 coins. And finally, I equals 3, so then we just finish using the pennies. D3 is 3, we need 3 pennies. So the output is D1 is 5, D2 is 1, D3 is 3. Okay, so to make change with these coins, we need 5 12s, 1 of the 7-cent coins, and 3 of the pennies. Alright, so that's, so just making change in pseudocode in this. So as we step from I going from 1 to R, so at each step we're just maximizing, so using as many of each type of coin as possible in each step. And that works as long as we start with the biggest coin first and go down. Alright, so that's our look at algorithms.